Hello and welcome to EC Electronics. So in this video, we are going to discuss about the static and dynamic chara of instruments. We have already done a video on the introduction video of electronic instruments and measurements. In that, we have discussed about the type of instrument and the basics of measurement, the type of measurement and all. In this video, we'll be discussing about the charas, which are the static and dynamic chara of the instruments. So let's see what are the static charas and what are the dynamic charas. So in today's video, we are going to discuss about the static and the dynamic chara of instruments. So we have already done a video on the category or the types of instruments which we use in electronic instruments and measurements subject, or we study under this subject. And today we'll be discussing about the static and dynamic chara or characteristics of these instruments. First, we are going to see the static chara. There are almost 12 static charas. First one is accuracy, second one is precision, third one is sensitivity, fourth one is linearity, fifth one is reproducibility, sixth one is repeatability, seventh one is resolution, eighth one is threshold, ninth one drift, 10 stability, 11 tolerance, 12 range or span. Now I'm sure that all of you have heard of these terms, but how can we define these terms in terms of the instrumentation, like a definition? How can we define for the instruments? Okay, so let's see, and we'll be discussing all these things in an exam point of view. Okay, so these 12 charas we are going to see, which are the static charas. So the first static chara is accuracy. Now what is accuracy? Accuracy means how much the reading is accurate, right? So accuracy can be defined as a degree with which the reading approaches the true value of the quantity to be measured. How much accurately we can get the measurement, how much accurately we are able to get the reading, that is the accuracy. Now we can say accuracy as three types: point accuracy, accuracy as percentage of scale or scale span, then accuracy as percentage of true value. So these three ways we can actually represent accuracy. Now first one is point accuracy means, so such accuracy is specified at only one particular point of scale. So if the accuracy or the reading we get as that exact point, we say that it is a point accuracy. Consider that the reading is exactly at one point, and only if we get that point, then we say that it is accurate. Such an accuracy is called point accuracy. Then the second one is accuracy as percentage of scale span. Now when the instrument has uniform scale, consider that the scale is a uniform scale of the instrument, its accuracy can be expressed in terms of the scale range, how much accurate it is according to the scale width. So that is called accuracy as percentage of scale span. Then third one is accuracy as a percentage of true value. Means here we are going to, it is actually the most precise way of saying accuracy. The third one, accuracy as a percentage of true value. How much we are able to get the correct value of the quantity which we are measuring. That is the true value. And how much is that, that is how can we represent accuracy as a percentage of this true value, is called the third category. Okay, so the three type of accuracies are point accuracy, accuracy as a percentage of scale span. Third one is we are going to actually represent accuracy as a percentage of the true value of the quantity which we are measuring. Okay, so true value means, consider that I'm going to read a resistance value. Okay, so this original value is 10 ohm, which is called the true value. Now while measuring, I may sometimes get it is 9 point something or 10 point something. So these are some variations, and the true value is 10. Okay, so this is the concept of true value, and we can also express accuracy as a percentage of this true value. That is the third category. Okay, now this is accuracy. The second static chara is precision. Precision means actually, in simple words, you can say precision as how precisely we are able to measure. Okay, so I'll take a small example, which is actually a classification of precision. Consider that your resistance value. This is a resistance value which is 2385692 is the resistance value, but the available scale is only 2.4 meg. Okay, but exact value is not 2.4, it is something less than 2.4 meg, but you are able to only read the value as 2.4 meg, which is due to the absence of that scale. Okay, so your reading scale is on meg, so you are only able to read it as 2.4 meg. So this is a precision error. Okay, so this is precision, how precisely you can read the value. Okay, so as a definition, you can say precision as the measure of the degree of agreement within a group of measurements. Okay, so precision is a measure of the degree of agreement within a group of measurements. You don't need to by heart these statements, but just know that the precision is a range, or how precisely we can make the measurement. Okay, now we can classify precision as two types. One is conformity, because due to the absence of this scale, we are not able to give the exact value or measure the exact value. Okay, so that is one precision error. Next, precision will also depend on the number of significant figures. Okay, so in how many number of significant figures we can do the measurement. So these are the two factors affecting the precision, and precision can be represented as P equal to 1 minus xn minus xn bar by xn bar in modulus. Okay, where xn is the nth measurement value and xn bar is the average of a set of measurements. So what is the disagreement of the nth measurement in that group? Its measure is called precision. Okay, so in simple words, you can say it or think it like how precisely we can make the measurements. Okay, so that is second characteristics, which is precision. The third static chara of instrument is sensitivity. So just like we normally say sensitive means, very sensitive means easily reactable, or in common saying we say like that, right? So that is sensitivity. Now for an instrument, the meaning is same, but we say it in a different way. Sensitivity is the smallest change in the measured variable which the instrument can respond to. Consider that there is a very slight change in the quantity which we are measuring. Okay, so whether your instrument responds to it or not. If it is responding, then we say that it is having high sensitivity. If it doesn't respond so quickly, means we say it is not really sensitive. Okay, so that is the definition for sensitivity. Also, 1 by sensitivity is called deflection factor. Now, let us analyze this sensitivity in terms of an equation. Sensitivity equal to delta Q0 by delta Qi, where Q0 is an infinitesimal, that is a very small change in output. Delta Qi is a very small change in input. So this change in output to change in input, very small change in output to small change in input, is called sensitivity. If you take two graphs, this is an output to input graph of two measurements or two devices. Here you can see that delta Qi is very large or comparatively large, and delta Q0 is small, means it is having less sensitivity. Denominator is larger and numerator is small, so sensitivity is less. Then delta here, if you see this graph, Qi is small and Q0 is large, means it is having numerator larger value, means it is having high sensitivity. Okay, so if you compare these two devices, this graph is having more sensitivity as compared to this graph. Okay, so that is sensitivity. The fourth characteristic is linearity. It is the ability to reproduce input chara symmetrically and linearly. Okay, so linearity is defined as the ability to reproduce the input characteristics, that is chara, symmetrically and linearly. We can explain this linearity with the help of a graph. So this is the idealized straight line which is explaining any of the chara of the quantity which we are measuring, and this is the actual curve. Okay, so this is the idealized straight line which we are actually expecting, but this is the actual curve, and this portion shows the maximum deviation. Okay, so maximum deviation means maximum change from the idealized straight line. So here the percentage of non-linearity we can express as maximum deviation of output from the idealized straight line to full scale reading. Okay, so linearity we can say in simple words is, consider any of the one chara of your quantity which you are measuring. If the device is able to reproduce that chara linearly and symmetrically, means we can say that the device is linear. Okay, so if there is any deviation, any large deviations from the chara, that is the ideal chara value, then we can find the non-linearity with this equation. So if the device is linear, means it will be producing the chara, and the chara will be having the same shape of this idealized straight line, but the actual curve will have certain non-linearities, and due to that this will be your actual curve. Not this in all cases, this is a sample or an example. So there can be variations or deviations from the ideal values which we are expecting. Okay, so this is called linearity of a instrument. Fifth chara is reproducibility. It is the degree of closeness with which a given value may be repeatedly measured. That is, it is specified in terms of the scale of reading over a given period. Okay, so how closely we can reproduce a given value or a given experiment. Okay, so that is reproducibility. Then sixth one is repeatability, means it is actually measuring the variations in the measurement taken by the instrument under same condition. Now these two sounds really closer, having same definitions, right? So the difference between these two is that reproducibility will be applicable or is said in terms of the entire experiment. Here we are going to repeat the entire experiment, and we are trying to reproduce the entire experiments under the same conditions. Okay, but here this repeatability is said in terms of a particular measurement only. Okay, so that is the difference. So repeatability is the measure of variation in the measurements taken by the same instrument under the same conditions. Okay, so that is repeatability. So here we are interested in taking a single measurement, but in reproducibility, there we are going to actually reproduce the entire experiment, and we will see how closer we are getting the readings. Okay, so that is the fifth and the sixth charas. The seventh chara is drift. So this drift is actually classified as three categories. So if you say a basic definition of drift, means it is actually some variation in the readings, some scale changes, okay, some variation in the scale. So that is the drift. So we can classify the drift as three categories: zero drift, span drift, and zonal drift. Zero drift means, so if the whole calibration shifts due to the slippage or due to the warming up of the electronic tube circuits, means your entire scale range is shifting upwards from the zero level, it is shifting upwards, means that is called as zero drift. So when the scale is changing, when your reading scale is changing entirely from the zero, then your all readings will have that variation. So that is the first zero drift. So here your entire scale is shifting upwards due to some errors. Okay, so that is the first category. Second one is span drift, means there is actually a proportional change. So when you are making a reading, there you can see a proportional variation. That is, you are expecting some values, but you are getting values different from this original value or the true value, and the changes that you are seeing in this measurement is proportional. Consider that your initial reading or your reading you expected is 32. First reading you got as 34, then you are getting as 36, then you are getting as 38, means there is a proportional variation in your reading, right? So this type of drift is called span drift. Okay, so it is a proportional change in the indication all along the upward scale. Then third one is zonal drift, means here the drift only occur in a portion of the span. Only in a particular range there is a drift happening. There is a scale change. Drift means a change in scale. Okay, so that is called zonal drift or zonal variation. So the eighth chara is resolution. Consider that if your input is increased from some arbitrary value, but the output doesn't changing until the input exceeds a certain range, and this range is called resolution. Or in simple words, you can say resolution is the minimum change in your input which is detectable. Only after that range, your output will detect your input change. Okay, so that is resolution. So just like the ADC resolution, we say the minimum change, that is the resolution here also. Okay. Ninth one is threshold. So we have discussed about threshold potential and threshold voltage, everything. Just like that, there is some standard value after which only the change is there, or till that value, even if your input is changing, your output won't get affected or won't produce a variation. But after that threshold, if the change is increasing or if the change is greater than that threshold value, then only your output will detect. That is threshold. Okay. So these two things, resolution and threshold, are a little bit connected. Then 10th one is stability. Stability is the ability of your instrument to retain its performance throughout the operating period. So even if it is producing stable outputs or stable readings, then it is called a stable instrument. Then tolerance, which is the 11th one, is a maximum allowable error. So just like in resistance, there is tolerance values, right? So the maximum allowable error in the instrument is called tolerance, which is the 11th chara. Then the 12th static chara is range or span of measurement. So this instrument is also having a span. It can have a minimum value which it can produce as output and a maximum value that it can give. Okay, so this difference in between the minimum and the maximum value is called the range of the instrument or the span of the instrument. Okay, so that is the 12th static charas. So these are the 12 static characteristics of the instrument. Now we are going to see the dynamic charas. Dynamic characteristics of an instrument. The first one is speed of response. Speed of response is the speed with which the measurement system or the instrument can respond. That is, it can respond to the change in the quantity which it is measuring. So how fastly it can respond or it can give output is called speed of response. Second one is measuring lag. Measuring lag means the delay in the response. Okay, so the opposite of speed of response is lag, which is the delay in the response. And there are two types of delays. First one is retardation delay, then or retardation lag. So this is actually lag. So retardation lag and time delay lag. So there are two types of lags. Okay, so the lags are of two types, retardation lag and time delay lag. So what is retardation lag means? Here the response of the instrument or the measurement system begins immediately after the quantity which it is measuring has changed. So it will respond but only after the quantity has changed its value. Okay, so that is the retardation lag. Then second one is time delay lag, means here the response of the instrument or the measurement system begins after a dead time. So there is a dead time after which only it will give the output. Consider that there is a dead time of 10 milliseconds. Only after this time it will start producing the output. So that is the second type of lag. Third one is, that is third chara is fidelity. So this fidelity is the ability to avoid dynamic errors. Okay. So it is defined as the degree to which a measurement system or an instrument indicate changes in measuring quantity without dynamic errors, or how can this instrument, or how good this instrument is at giving you outputs in response to the change in the quantity which it is measuring. Consider that an instrument A is measuring a quantity B. So how good this instrument A is at giving the changes in B without dynamic errors. Okay. So in short, we can say how good A is at avoiding dynamic errors. That is the fidelity. Then fourth one is dynamic error. So this dynamic error can be said as a difference between the true value and the measured value of the quantity, assuming that there is no static errors. Okay. Also, the dynamic error can be called as measurement error. So this is a dynamic thing. When the measuring is happening, then what error can happen? That is a dynamic error. Okay, so the errors happening during the measurements is called dynamic errors, and at that time we are not taking into consideration the static errors. Okay, so these are the 4 dynamic errors of the instrument. So in this video we have discussed about the static errors. There are 12 static errors and 4 dynamic errors. These are the important ones. There are also some other terms, but the most important ones are these 12 static and this 4 dynamic errors. Okay, so I really hope that you understood the concept of the errors, static and dynamic. If yes, please do give it a thumbs up and also share it with your friends who's preparing for this ISRO technical assistant examination and all those diploma exams specially, because for those exams this electronic instrumentation and measurement is a very important subject. Okay, and if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.